Hello, my dear students. Just to keep you up to date, I'm still quarantining at home with my son Joseph, who had exposure to a person with a known positive test. And to date, he has shown absolutely no symptoms except normal boyhood rambunctiousness and everything. So we are doing fine. I want to take today and do a little screencast, go to our class, and talk about the System International de Units for the units we're going to be using in chemistry. If you open this up, it may not show up very well until you save it in a different format and open it in PowerPoint or something else. You notice the first time I opened up, it didn't open up with the figures. You're welcome to listen to this and watch this and follow along at the same time you watch or use the lecture notes that have been posted in a different window or on a different device. So, as I mentioned before, if you do not include units, your answer will not be counted correct. And I guess I can agree with them that there are 5 common units that chemists use, but I don't know about them being base units. Indeed, some of them are derived units. But there is an international system, in French, the Système International, that chemists use to define all units, and all units are derived from 7 base units. And you see those now in front of you. They're length, mass, temperature, time, amount of substance, luminous intensity, and electric current. And you probably have come across almost all of these in one form or another. Everyone has seen a meter stick. Everyone knows about kilograms and grams. And they're, different forms of the same unit in different multiples or divisions thereof. You may not have heard of the Kelvin, which I like to spell with a capital K, abbreviated capital K. It's named after Lord Kelvin, a famous scientist. However, you will know that it is the same as a degree Celsius in unit size, if not the difference being where the temperature scale starts and stops. Everyone's dealt with seconds. You may not have heard of moles, but it's a fundamental unit of the amount of matter present that we'll be using. And in America, I guess we tend to use lumens instead of candela, or in old terms, candle power. And the electric current, of course, is the amp. So, the units we're going to be using as a chemist, I can think of some others, but length, volume, mass, temperature, and energy. And volume, of course, is not a base unit, it's a derived unit. I'll show you what I mean. So, everyone knows about length, and the basic unit of length is the meter. It was originally defined as 1/10,000,000th of the distance from the equator to the North Pole, but is now defined based on wavelengths of certain emission spectra in certain elements. I want to say krypton. And I think even that has been further refined. Most recently, I want to say last year. Now, as the amount of the distance light travels in one oscillation of some atom or something. Some very sophisticated techniques to do it. But meters are not very useful. If I want to say how far is it to Little Rock, and I don't want to tell somebody it's 116,000 meters, I use the kilometer, okay, which is 1,000 meters. And, of course, for very small measurements, it wouldn't be very practical to use meters, because then I would have to start using negative exponents or many zeros in my fractions. So you've dealt with centimeters before. It's a common measurement. There's 2.54 centimeters to an inch. if you want another reference. And of course, the millimeter lines are the lines on the smallest lines on a metric ruler. And of course, in chemistry, when we're going to be measuring very, very small atoms, we need some much smaller values like the micrometer and the nanometer. We'll cover them as we come to them. Now, volume is a derived unit, and of course, by derived, I mean it's derived from the meter, from distance, because what is volume? Length times width times height. However, as you'll see when we talk about a sample problem, that gives you new units, which are meters cubed or centimeters cubed. And if you consider the most common, in the base, I guess not the base unit, but the most commonly used measurement of volume being the liter, it's the volume of a cube that is 10 centimeters on edge. And of course, that would be 10 times 10 times 10, or 1,000 cubic centimeters, and that would equal 1 liter. We'll also be using milliliters. It's a very common value. It's equal to about 20 drops of water. That's the same thing as the cubic centimeter, abbreviated centimeters cubed, or archaically cc's. You hear that sometimes with engine displacements and in old shows where that deal with medicine, and a medical doctor will say, push 10 cc's of bicarbonate or something, and that's an easy unit to make mistakes with. So all medicines at all pharmacies and in all physicians' offices now are measured in milliliters, although it's equivalent to a cubic centimeter. Of course, we'd be dealing with very small volumes, microliters, depending on the experimental situation. Now, unit of mass, the standard is the kilogram. It was originally defined as the weight of a platinum iridium cylinder in the Bureau of Standards in Europe, in the City of Science in the city of Paris. I've actually had the pleasure of going there and seeing it. It now has a different definition, actually as of last year, that is itself, again, a derived value that relies on some of the others. But a kilogram is approximately 2.2 pounds, and common measurements we'll use in chemistry are the gram. It says here a dollar bill weighs about a gram. I don't think that's quite true. I think it weighs a little less, but and the milligram, many drugs are dispensed in milligrams, and the microgram, which gets us into units that we frequently have to use in chemistry because some of our tests are so sensitive and we can detect increasingly smaller amounts of materials. So we'll be using the gram and the milligram predominantly in this course, including in an experiment we'll be doing later this week. Now, weight and mass are used interchangeably, perhaps too frequently in chemistry and never in physics, but weight is a force. And technically, sometimes I'll have to correct myself. When I say weight, I actually more correctly mean mass. And for the most part, they're interchangeable. But weight is a force. It's mass times the acceleration due to gravity. And, of course, if you're under a different gravitational force, as in the moon versus the Earth, you will have a different weight, although your mass did not change. But we'll leave the problems and the refinements on that to physics. Temperature is measured with a thermometer. It's a measure of how hot or how cold an object is. And we're going to use the Celsius scale, where conveniently the scale is divided into 100 equal divisions, where you have 0 being the freezing point of water, and 100 the boiling point. We also find it convenient in chemistry to use the Kelvin scale. And in this case, the Kelvin unit, the degree Kelvin, although we're not supposed to say degree Kelvin, it's just a Kelvin now. We still say a degree Celsius, but it's just a Kelvin, not a degree Kelvin. The Kelvin and the degree Celsius have the same magnitude. They're equal to one another. But the scales are different because they start at different points. Celsius, like I said, the 0 degree point is the freezing point of water. On the Kelvin scale, the 0 degree point is a point we term absolute zero. That's the point at which there is no heat in the system and all molecular motion stops. We've never been to or achieved absolute zero, but we've been within a few, not even a few, less than 1,000th of a degree of it. But the difference is the Kelvin scale at 0 would be equal to minus 273, technically 273.15 degrees Celsius. And we will work a problem with that in our section review. So, as long as we're talking about temperature and the like, let's talk about energy. Heat energy being one form. Energy is capacity to do work. Sometimes that work may be to produce heat. And we commonly use the joule, although we'll also be using the calorie. And this calorie is not the same as the calorie we talk about in human biology and in nutrition. When you look at how many calories something has on the side of the package, for example, a can of Coke, that calorie is technically a kilocalorie or 1,000 of the calories we're talking about here. And a calorie and a joule are derived units, and let me tell you what that means. That means they are not what you call base units. They are derived from the other units. A calorie is the quantity of heat required to raise 1 gram or 1 milliliter or 1 cubic centimeter, those are all the same thing, of pure water by 1 degree Celsius. And by being the same thing, those aren't the same thing, but 1 milliliter of water weighs 1 gram. And so that's a calorie. And of course, there are 4.184 joules per calorie. We'll worry about that much later in the course when we get to thermodynamics. So all I wanted to do was to briefly mention one aspect of your homework, and that is, if you look at the new assignment, it has, here it comes, it has some problems at the end. And those problems include several conversions. And that is, what is the volume of a board, in question 28, that measures 1.8 by 8.8 by 30.5 centimeters? There's only one thing you need to look out for here. Of course, this board is basically a rectangular solid, and you would get the volume by measuring the length times the width times the height. So you would do 30.5 by the width, 8.8, by the height or thickness of the board by 1.8. And when you get that answer, don't forget, you also multiplied centimeter times centimeter times centimeter to get centimeters cubed or cubic centimeters as your units. When I say hydrogen boils at 20 K and they want to know what's the boiling point of hydrogen on the Celsius scale, well, that's really, really cold temperature. And you would simply take that 20 and subtract from it the 273 degree difference between 0 on the Celsius scale and 0 on the Kelvin scale. So your answer would be 20 minus 273, you do the math, and the answer is degrees Celsius, or the units would be degrees Celsius. And then this is some practice with some of the prefixes or prefixes, however you wish to pronounce it, in our metric system. You should know them. You need to learn them. We'll cover them and use them as we do. Centi refers to 1/100th, as in century has 100 years. Kilo is kilometer is a times 1,000. Micro would be 1/1,000,000th, or 10 to the minus 6th. And pico would be 10 to the minus 9th, or 1/1,000,000,000th. So some of the other ones to know are milli, 1/1000th. And of course, most people know the ones going up the scale. We used to have kilobytes, and then we have megabytes, and now we have what? Gigabytes and terabytes. And each one of those increases by 10 to the third, or 1,000. So review those, and thank you for listening and watching, and I will see you on the next one. Take care and stay safe.